Good afternoon. My name is Maja and I have been a PhD candidate at the Department of Psychology and RITMO here in Oslo for the past 4 years. I have been investigating adjustment of attention to rapid dynamics in auditory rhythms. Temporal aspects of attention have been much less studied compared to spatial and feature-based attention, meaning that its underlying neural mechanisms remains poorly understood. Today I will present a study that aims to shed light on this issue. In this study, we focused on a well-known index of spatial attention that is based on the assumed functional role of alpha and beta oscillations. Activity in these frequency bands is often shown to be inversely related to cortical processing, meaning that suppression is associated with enhanced neural processing. Accordingly, studies where participants direct attention to the left or the right ear typically reveal alpha or beta suppression contralateral to the attended ear, and this is due to stronger contralateral pathways in the sensory system. This effect can be represented in topographical plots like the one to the left, which represents the relative difference in power between attend left and attend right conditions. Accordingly, one will get positive values over the left hemisphere, suggesting reduced alpha power during attend right conditions, and negative values over the right hemisphere, suggesting reduced alpha power during attend left conditions. While this effect is often seen for the alpha band, it sometimes also involves the beta band. It has been proposed that beta band oscillations might specifically support temporal aspects of attention, while the alpha band might be involved in attention to other features of the stimuli. However, this remains to be investigated. It is also suggested that modulation of beta oscillations during temporal orienting could result from top-down prediction of temporal structure. For instance, in this study by Van Ede and colleagues, participants either expected a tactile stimulus at one of 3 or one of 2 time points. Here they found that the time course of lateralization differed between these 2 timing conditions, but only in the beta band. This suggests that beta band modulations might reflect expectations regarding the timing of forthcoming stimuli. However, as the temporal expectancy in this study was used to manipulate temporal attention, it is not possible to disentangle effects of stimulus predictability from stimulus relevance. Finally, there is a lack of studies investigating the ongoing dynamics of attention. Nonetheless, in one study by Blenkmann and colleagues, it was demonstrated that alpha lateralization fluctuates according to the presentation rate of the stimuli presented to the attended and unattended ear. However, as the attended and unattended stimuli were presented simultaneously, it remains unknown whether these fluctuations reflect voluntary control of attention to the timing in auditory stimuli. The present study had 3 main goals. First, we investigated modulation of alpha and beta activity during a task that involves making decisions regarding sound timing and not any other stimulus features. Based on the proposed specific role of beta oscillations in timing-related aspects of attention, we assumed attention modulation to be stronger for the beta band. Second, we independently manipulated rhythm predictability from temporal attention. Given that beta oscillations are involved in the prediction of temporal structure, we expected to see enhanced lateralized beta modulation with increased rhythm predictability. Finally, we addressed whether fluctuations of alpha-beta lateralization are under top-down attentional control. We hypothesized that when stimuli differ in presentation rates between the left and right ear, lateralization will synchronize with stimuli presented to the attended and not the unattended ear. And so we presented participants with repeating rhythmic sound sequences, which could be treated as 2 separate rhythms with different presentation rates. indicated by the blue and the red bars. The two rhythms were presented to separate ears. During each block, participants attended to the rhythm in one ear and were asked to respond each time a tone in the attended rhythm appeared too early, which I will refer to as time deviances. To investigate lateralization of alpha and beta power, we subtracted the power during attend right conditions from the power during attend left conditions. To independently manipulate rhythm predictability, we ran each of these 4 blocks twice. Once, where the number of sequences containing time deviance were rare, denoting high rhythm predictability blocks. In the low predictability blocks, sequences containing time deviances occurred more frequently. Finally, we assessed fluctuations in the time courses of the lateralization during blocks where participants were attending the slow as well as the faster tempo. For both the alpha and the beta band, we compared the difference in attention modulation between the left and the right hemisphere. The results revealed a significant difference between hemispheres only for the beta band. This was evident for both scalp data and source reconstructed data shown to the left. As shown in the figures, the effect was reflected by positive values over the left and negative values over the right hemisphere. With no significant effects for the alpha band, the remaining analyses were performed for the beta band only. And to assess effects of rhythm predictability, we computed attention modulation for the high and low rhythm predictability blocks separately. We then computed attention modulation strength in each predictability condition as the difference between the two hemispheres. When comparing the attention modulation strength between the high and the low predictability condition, we found a significant difference for scalp level data. The effect was reflected in greater attention modulation during high predictability blocks where time deviance were rare. Finally, we addressed synchronization of lateralized activity with attended tempo. Lateralization in each trial was therefore computed as the relative difference in power between the two hemispheres, which was performed for each time point across the rhythm sequence. The y-axis of the figure denotes the degree of lateralization, and the time courses of lateralization during attending the slower and the faster tempo is presented. A circular Rayleigh test revealed significant phase concentration at the attended presentation rates, that being the faster or the slower tempo. On the contrary, results revealed no significant phase concentration at the unattended presentation rates. Put simply, the results suggest that fluctuations in beta-lateralization synchronize more strongly with the attended than the unattended presentation rates. Related to our first goal, in the present study we have demonstrated that when a spatial attention task involves decisions regarding sound timing only, this results in lateralized beta and not alpha oscillatory activity. This supports the idea that beta oscillations might serve a specific role in temporal aspects of attention. Secondly, rhythm predictability was independently manipulated from temporal attention. Our result therefore suggests that top-down prediction might enhance temporal orienting and that this does not result from a change in the relevance of sound timing, as this remains constant across all conditions. Finally, related to the third goal, we show that when attended and unattended stimuli are presented simultaneously but with different presentation rates, lateralized beta activity synchronizes with the timing of attended and not unattended sound stimuli, which suggests that ongoing dynamics in lateralized beta activity is under top-down attentional control. Thank you so much for listening, and of course, thanks so much to my colleagues who contributed to this study.